Evening everyone, and welcome back to the tutorial 8 of this course Surface Water Hydrology. Before going to the problems of tutorial 8, we were left with one topic in the previous tutorial 7, which is instantaneous unit hydrograph. You may have watched the videos. So what is actually an instantaneous unit hydrograph is? So earlier we went through what is a hydrograph, and then we studied hydrographs of different duration. Then we did problems on unit hydrograph, then different durations of unit hydrograph. So we had 5-hour unit hydrograph, 10-hour unit hydrograph, 2-hour unit hydrograph, which was represented, the duration was represented by T. And now let's say this D tends to 0. The hydrograph we get is called an instantaneous unit hydrograph. So from now onwards, I will write it as IUH. So this has some properties. One is that it will be having a single peak. Another thing is that it will be going to have a finite base, so which will actually represent the surface runoff from the catchment due to instantaneous rainfall, and that rainfall has a unit of or a magnitude of 1 centimeter. So the effective rainfall is going to be 1 centimeter, and we are trying to find the surface runoff from the catchment instantaneously due to this rainfall. So there are few properties which I will write here. Let's say this ordinate of the unit hydrograph is to be represented by U of T. So the U of T, so this has been taught in class, but I will try to recall it, is less than A for T is greater than 0. So whenever the time is greater than 0, your coordinate is going to be positive quantity between 0 to A. So here A is positive. And the second thing is that U of T is 0 for T less than equal to 0. And similarly, U of T will tend to 0 as T will tend to infinity. And the last property of it, which is the property of every unit hydrograph, is that if you integrate the ordinates of UT or find the area under the unit hydrograph, you get a unit depth, which is actually representing ER over the catchment, effective rainfall. Now, let's say you have effective rainfall, which is represents I tau of duration T naught. Then your Q of T, which is your direct runoff from the catchment. In terms of in the instantaneous unit hydrograph is being represented as an integral of U of T minus tau into I of tau d tau. So this part is called as an convolution integral. Just a recap of these things. And then T dash is T when the T is less than T naught, and similarly T dash is to be 0 when T is greater than T naught. So the important thing is we will try to derive this instantaneous unit hydrograph. So there are different ways. One way is that we can derive it using S-curve. So there are some steps which we need to follow to derive the instantaneous unit hydrograph, given that we know the S-curve of that catchment or the storm. So let's consider a S curve S1. Yep. So we considering, sorry for there was some technical issue. So we now consider another S curve S2, which has the same intensity I, and then S2 is to be separated from S1. So by the time interval dt. Earlier, when we were trying to identify or calculate the unit hydrograph from the S curve, we used to lag that S curve by the duration of the hydrograph which was needed to be calculated. Here that duration is dt because we are focused on instantaneous unit hydrograph, and ordinates are to be subtracted. So we get a DRH whose rainfall is rainfall, I can say rainfall excess has duration dt and magnitude I dt, or we can say dt by capital D because I is 1 by D. So a unit hydrograph of dt is then obtained. We can obtain it by simply dividing by the required DRH that we have computed by IDT. So you have a DRH, you divide it by IDT, you get a unit hydrograph of DTH duration. So let's say I can write it in this way. The S1 ordinate to be represented by S1 and S2 by S2. We can write S2 minus S1 and divide IDTH. And now we know that this duration in the instantaneous unit hydrograph is tending to 0. So we can write it as U of t is actually limit dt tending to 0 S2 minus S1 divided by IDT, which is 1 by I ts by dt. So if let's say I is 1, then U of t is directly ds of dt. So this simply means if you try to find the slope of S curve, you get an ordinate of instantaneous unit hydrograph. Now we are going to do a problem on this. Let's say we are given the ordinates of S curve of an catchment with the rainfall intensity to be 2 centimeter per hour. So this was already shown in the class. I will try to explain it furthermore. So you are given the time interval. Your time interval is delta t is 0.5 hours. S curve is given in meter cube per second. We need to derive the instantaneous unit hydrograph from this catchment. So if I write what we found earlier, U of t is to be 1 by I d of st divided by d of t. So your I is given to be 2 centimeters. So this will be 1 by 2 ds of t divided by d of t. This can be 1 by 2. And d of s of t is the change in s ordinate or the s curve with time. So let's say how we can do here is we have a time step 0.5, 1, 1.5, 2, 2.5. Now let's say I need to calculate this change as this time step. We consider it as t because we are need to find u of t here. So this is time step t. This we can consider t minus delta t, and this is t plus delta t. So ds of t can be calculated using these 2 points. So I can write s of t plus delta t. This is also called the method of central difference. There are other methods, so like method of forward difference and backward difference, and delta t will be the t plus delta t minus t minus delta t, change in time. So this is 1 by 2 s of t plus delta t minus s of t minus delta t divided by dt will go, and this will be twice delta t. Now let's say you have corresponding to 1 you have a value of 150, 1.5 you have a value of 300, and here you have a value of 450. So now let's say at this time step I need to find u of t. So u of 1.5 will be equal to 1 half of, so s of t plus delta t will be the value of 450, and minus the value of st minus delta t will be 150 divided by 2 into delta t, time difference is 0.5 hours for the time step. So this will be 1 by 2. 450 minus 150 is 300. 2 into 0.5 is 1. If you divide it, you get a value of 150 meter cube per second. And similarly, we can find this u for each time step. So I can show the calculation in Excel. Share the screen. So here is your S curve, time, and here is your S curve in meter cube per second. So in a instantaneous unit hydrograph, what we found is, let's say we calculate here, it's the, start with the bracket, the value of S curve at t plus delta t minus the S curve at t minus delta t, and you need to divide it by 2. So you get the value of 75 here, and similarly you can drag the value, you get a value of corresponding to 1.5, what we found is 150, you get a value of 150. You can put a value of 0 here. Now we can analyze this plot. Here it's going to be 0. So this is your plot, this is your S curve whose data was given, and we found the instantaneous unit hydrograph corresponding to this S curve. So any questions on this problem? I think it's straightforward as we did in the unit hydrograph derivation from S curve also. The only thing that's different here is that your delta t is very small, whereas in that case delta t used to be the duration of hydrograph which was needed to be calculated. So if not, then we can go to the tutorial number 8, in which you are taught about floods. So floods is just, we can say it's an overflow of water, or some may say it is high stage or the level of water in a river. There are different types of floods that can occur. I will just write them. One is riverine flood, another is your flash flood, then you have a coastal flood, then the storm surge, and then you have an urban flood. But what's more important in the floods is to first understand what characteristics of floods we should study and which are important in terms of prediction and in terms of how we can save people or the property, or we can say it in early warning system. So I can write as an attribution of flood. So let's say this is your flood unit hydrograph. This is your discharge flood unit hydrograph or flood hydrograph. I can write hydrograph, better to write hydrograph. And this is your duration of this flood hydrograph. And now this point, what we studied earlier, this is also called the peak flood magnitude. Similarly, this is going to be the duration of this flood. And the third property is, let's say this is your base flow, you can have, is the area under this curve, which will be giving you volume of the water or volume of the flood volume, I can say. That is actually the area under the curve. So three properties or three attributions I can say. One is flood peak. Second is going to be your flood volume. Third is going to be your flood duration. Now in this flood peak, you can represent this peak either by the depth of water, that's in mm, meter or centimeter, and this is what you call as stage also. The second way you can represent it is actually you represent the magnitude of discharge corresponding to this time step, and this will be in the units of either meter cube per second or some other units. Now in this tutorial we will be mostly focused on peak flood magnitude, and we will try to see how we can compute this peak flood magnitude. One of the ways we can compute is using the rational method. This all has been covered in your lecture notes. I am just giving you a quick recap so that it becomes very easy to go with the problems. So this is one method to estimate peak discharge during a flow. So this equation is the peak discharge is represented by CIA when time is greater than the time of concentration. To explain it in more nice way, you have just like this is your unit hydrograph or runoff on the y-axis, and here you have the time. Now let's say there is a precipitation happening, and when the precipitation starts from time t is equal to 0, your runoff starts increasing and it reaches to some level. At this point, after this point, the runoff becomes constant. This is the point when the whole catchment starts contributing, or we can say this is the time of concentration. So the most remote point of the catchment also starts contributing to the runoff. After this, your runoff becomes constant, and when the precipitation stops, your runoff starts decreasing, what we call as recession. We have covered in the first lecture only on the hydrograph, we covered how we can model this recession curve, if you recall. So the equation is Ci into A, and this is only applicable when your time is greater than Tc. After this only the peak is reached. Before this T is less than Tc, this peak is not reached because all parts of the catchment are not contributing to the runoff. So this C is your runoff coefficient. I is your intensity of storm or rainfall, and A is the area of catchment. So yeah, and now this QP can also be written in the form of 1 divided by 3.6 C into I into A, So if you convert the units where I will be in the millimeter per hour, here it's I think centimeter per hour, and this runoff coefficient remains C as such, and area is kilometer square. So QP will be in meter cube per second. So, but the important thing is here that we need to calculate first TC, that's the time of concentration. And for the time of concentration, we have different equations. So one of the methods is based on US practice, what is being practiced in US. So their TC is equal to the TP. So if you recall, your TP is exactly the time of peak flow. This we studied in previous class, and this was computed as CTL, L into LCA divided by root of S for raised power n. And similarly, your second method is Lipschitz equation. Your TC will be 0.01947, L raised power 0.77, and S raised power minus 0.385. So this is in minutes. L is defined as maximum length of travel of water. This has to be taken in meters, and this is slope of catchment. And this is delta H upon L. Now, if you look into the equation, so one thing we found is the TC, which is the time of concentration, but we also need to find the intensity of rainfall. I can write rainfall intensity I TC comma P. This is your rainfall intensity, and this is written as KT whole raised power X. This is one of the ways you can calculate it, TC upon A whole raised power N. Now this K, A, X and N are the coefficients in this equation, but these are specific for a given catchment. And similarly, you have runoff coefficient, which you need to compute, which is C. So this actually represents the overall effect of the catchment losses. So when we talk the effect of the catchment losses, so this will in turn be function of the type of surface, the surface slope and the rainfall intensity. And now let's say you have a catchment, and your catchment has sub portions which respond differently. In those cases, let's say this has runoff coefficient of C1, C2, C3, C4, C5, C6, C7, so and so on. So in these catchments, we try to calculate equivalent runoff quotient, which is calculated as summation of Ci into Ai. So this will be multiplied with its respective area, or we can say a weighted area mean 1 to n, and this way you can compute for the different heterogeneous surfaces, we can compute the runoff coefficients. And your equation, which is QP CIA 1 divided by 3.6, you can put the values of C, I and A to compute the peak runoff. Now we can do a problem on this. Now in this problem, you are given an urban catchment that has an area of 85 hectare. The slope of the catchment is given, so it's 0.006, and the maximum length of travel of water is also given, so your L is also given. The maximum depth of rainfall for a 20-year return period is as follows, as below. So you are given as a duration, you are given as a depth of rainfall. So if we if a culvert for drainage at an outlet of this area is to be designed, we need to design a culvert for this whose return period is to be 25 years. We need to estimate the required peak flow by assuming a runoff coefficient of 0.3. Now, the first thing that comes is the time of concentration that we earlier were discussing. So for the time of concentration, which is Tc, we can use the equation that was 0.01947 into L raised power 0.77 S raised power minus 0.385. Yeah. So your L in this case is the maximum length of the water, which is 50 meter, and your S, which is the slope of the catchment, is given as 0.06. So you can compute Tc by putting these values. Remember, the Tc will be in minutes. So 947 into 950, 4 is power 0.77, and S will be 0.006, 4 is power minus 0.385. You get a value of 27.4 minutes. Now what actually you know is an time of concentration. This is going to correspond to the peak intensity also after this, and we need to find the rainfall corresponding to this time period. So you are given the duration 5, 10, 20 and 30. So 27.4 will be lying between 20 and 30. We need to find the corresponding rainfall depth first. So this can be found by using interpolation method. So you have value 5, 10, 20, 30. On the rainfall side, you have value of 70, 26, 40 and this is time. This is the rain. Your 27.4 lies here, and let's say we need to find rainfall here. Let's say the value is X, or let's say value is Y. Y is better to use. So this can be found using an interpolation method, simple linear interpolation. So we know the equation of straight line between 2 points, y minus y1 is equal to y2 minus y1, x2 minus x1 into x minus x1. Now y2 can be considered 50, then x2 will be 30. Similarly, y1 will be 40 and x1 will be 20. Your x is 27.4, you need to find y. So if you put the values here, you get a value y minus 40 will be equal to 50 minus 40 divided by 30 minus 20 and x, which is 27.4 minus x1, which is 20. So you calculate this value. This will be 7.4 because 10 and 10 will go. So y will be 40 plus 7.4. So this will be 47.4 mm. The precipitation corresponding to 27.4 minute. So now the average intensity, since this is in mm, is simply the rainfall divided by its duration. Your rainfall is 47.4 mm, and this is corresponding to the duration of 27.4 minutes. So if you compute, it will come equal to 138 mm per hour. Now this is your ITC comma P, precipitation corresponding to the time of concentration Tc. Your QP equation is 1 by 3.6 into the runoff coefficient into the average intensity of rainfall into area. This was in mm per hour and this was in kilometer square. You get an QP value of meter cube per second. So this I can write 1 divided by 3.6. Your C coefficient in the equation is given. If you go, it's given as 0.3 runoff coefficient. Your I calculated in mm per hour is 103.8. Your area of catchment is 85 hectare. So A is actually 85 hectare. You can convert it into kilometer square by directly dividing by 100, which is 0.85 kilometer square. This is 0.85 kilometers. The value comes out to be 7.35 meter cube per second. So this is going to be the peak discharge, and for this discharge you need to design the culvert in this problem. So any doubts? So if not, then we can move to the problem number 3. Now we can start with the problem 3. In this problem, in an urban area of example previous one, example 2, the land use of the area and the corresponding runoff coefficients are given. So the previous case C was given, but now it's given that the catchment has roads. Let's say this is road, these are lawns, this is residential area, and this is industrial area. And we need to calculate the equivalent runoff coefficient. So we know this equivalent runoff coefficient is calculated by taking the weighted areal average of all the sub parts of the catchment, which is obtained by multiplying the area with its runoff coefficient C divided by the total area. So you have here 4 areas and their runoff coefficients are here. We can start with the calculation. So your equivalent runoff coefficient, which is to be, let me call it CE. This will be equal to summation CI AI upon A. So now you have four parts of this catchment. Let's say call it 1, 2, 3, 4. This is C1A1 plus C2A2 plus C3A3 plus C4A4 divided by A1 plus A2 plus A3 plus A4. Now if you look into the problem, so this is your A1, A2, A3, A4. This is going to be your C1, C2, C3, and C4. So you can put the values here. This will be 0.7 into 8 plus 0.1 into 17 plus 0.3 into 50 plus 0.8 into 10. So the total area will be 8 plus 17 plus 50 plus 10. If you do the calculation of this will be 30.3 divided by 85, which is equal to 0.36. So this is going to be your equivalent runoff coefficient. So now we can go to the problem number 4. So in this problem, you are given a 500 hectare watershed whose land use and current corresponding runoff coefficients are given here. So this is your area and these are your runoff coefficient. So it includes forest, pasture, and cultivated land. The maximum length of the water in the watershed is given as 3000 meter, which is L, and the elevation difference between the highest and outlet point in the watershed is 25. So del S, if I write, is del H upon L. So del H is given as 25. The maximum intensity duration relationship in the catchment is what we learned earlier. So this is I KT whole raised power X divided by TC plus A whole raised power N. Now this I is intensity, T is the return period, D is the duration, and we need to estimate 25-year peak runoff for the watershed. In the second part, we have to estimate 25-year peak runoff if the forest cover has decreased by 250 hectare and the cultivated land has encroached upon the pasture and forest land to have a total coverage of 450 hectare. So start with the solution. So we know the peak runoff equation, which is 1 divided by 3.6 into C TC of I into A into the intensity of rainfall. Sorry, C into TC into P. Now, so we need to calculate the runoff coefficient. Area is given, and then we also need an intensity of rainfall. So case 1, which is the first case. So we'll find the CE equivalent runoff coefficient as we found in the previous problem. This will be summation of CI AI upon A. So if you calculate it, it will be 0.1 into 250 plus 0.11 into 50 plus 0.3 into 200, and you divide it by total area, which is 500. So this comes around 0.818. Now we know that TC, which is time of concentration, the equation is 0.01947. K whole raised power K1 whole raised power 0.77. So earlier we had actual equation is 0.01947. Then you had here, I think, yeah, it was L raised power 0.77 and S raised power minus 0.355. So here this equation can be written in this form also, where K1 is under root of L cube upon del H. Now L, we know its value is 3000 meter and del H is 25 meter. So K1 can be computed. It's under root of 3000 cube divided by 25. So if you calculate its value, it will come 32863. And we can put this K1 here in the TC. So TC is 0.01947 into 32863, 4 is for 0.77. If you compute the value, this will be equal to 58.5 minutes. So as we know, TC is minutes. Now you can convert these minutes into hours. So this will come around 0.975 by dividing by 16. The minutes will get into hours. Now the second important thing is the calculation of intensity of rainfall, which is ITCP. So we know that TC is 0.975 hours and return period is 25 years. We have to use equation I, which 6 point, if we recall the equation, it's actually K T raised power X divided by TC plus A whole raised power N. Now the coefficients are given in the equation in the question. The K is given, it's not written here, but I will write the values. So K is 6.316. Return period, we know it's 25 years, and X is also given, it's 0.1523. PC we have computed 0.975. A is given in the question, it's 0.5, and the N can be taken as 0.977. So if you compute this value, it's 71.23 mm per hour. Now we can compute the peak flow, whose equation is 1 by 3 C equivalent intensity of rainfall into area. So this is 1.361 divided by 3.6 into C equivalent we calculated was 1.81. The intensity of rainfall now is 71.23. So this has to be in mm per hour, and the area has to be in kilometer per square, but it's given 500 hectare. We can divide it by 100 to compute it in kilometer square. So the value will be 64.46 meter cube per second. Now in the case second, where it's mentioned that if you go back to the problem, that the forest cover has decreased to 500 hectare, sorry, 50 hectare. So now this is 50 hectare here, and cultivated land has increased, and this has reached a total coverage of 450. So now the thing that will change from these altering this land use land cover is it will change the runoff coefficient. So we again need to calculate the runoff coefficient, but it's important to note that all the pasture land that we had is now in the cultivated land. So this is gone, this is 0, this will be 50, and the rest of 200 will be included into the cultivated land. So this is 50, I can write it here, this is going to be 50 hectare, 0 hectare, and then we have 450 hectare. So this is your forest, this is pasture, this is cultivated land. We can compute C equivalent, so equivalent runoff coefficient, this will be, this has an runoff coefficient of 0.1, this has 0.11, and this has 0.3. It will be 0.1 times the area of forest plus 0 into 0.11 plus 450 hectare into 0.3 divided by total area is again 500 hectare. So you do the computation, you get a value of C equivalent is 0.28. Now if you calculate the runoff again, which is the same equation, C into I into the area, so intensity will remain same, area of the catchment is also same. The only thing that's changing is the equivalent runoff coefficient, and you can calculate by putting here 0.28 and the intensity of rainfall to be 71.23 that we computed earlier mm per hour, and the area to be 5 kilometers square. You get a value of around 99.72 meter cube per second. So the only thing that has changed is that when your runoff coefficient is increasing, the peak discharge is going to increase linearly because it's multiplied linearly here. So any questions on this problem? So if not, then I can start with the next topic. That's we now estimate the peak flow using an empirical equations or empirical formulas. So this is so this empirical formula are derived based on some statistical relationships. Now let's say one of the common relationship that we have, or the simplest relationship that we have of the peak flood flow is with the area of the catchment. That's called flood peak area relationship. So in this, your maximum flood or the peak flood is to be assumed as a function of catchment area. So for different regions or different catchments, these empirical equations have been derived. One of such equation is Dakin's formula. So in this QP, which is the peak discharge in meter cube per second, is equal to the coefficient CD into area, 4 is for 3 by 4. Here area is in kilometer square. Now this coefficient is called Dickens coefficient constant. This actually ranges from 6 to 30. Similarly, other equation we have is Rayleigh's formula. And this QP is estimated as CR into area is about 2 by 3. Now here CR, again the QP is in meter cube per second. Area is to be in kilometer square. Now the CR has a value of 6.8. So this is basically this equation applicable in other regions for the watersheds or catchments in Tamil Nadu. Now this CR has been calculated. Let's say you are 80 kilometer, your catchment is 80 kilometer away from east coast. Then you need to take a value of 6.8, and you have to take a value of 8.5 if your catchment is 80 to 160 kilometer away from east coast. And otherwise you have to take 10.2 if it's near hills. Now this is the second one, and the third one is English formula. So this formula is mainly applicable on the Western Ghats, that of Maharashtra, and your peak flow is determined by an equation 124 into area divided by under root of A plus 10.4. Area is to be taken in kilometer square. Your QP is to be taken in meter cube per second. And after this, the way to determine the peak runoff is by the envelope curve. So this is actually if the catchments have a similar characteristics or behavior or climatological characteristics, and they behave in a similar way. So in those cases, what we do is we take the peak runoff of all catchments. Let's say you have 10 catchments, 100 catchments, whatsoever be the number. You take the peak flow of all the catchments. Let's say this is your peak flow, and then plot it with respect to the area of the catchment. So let's say this is your plot. So this is going to be the area x-axis, and the y-axis is going to be the peak discharge. Each point is corresponding to each catchment. Then you fit a line to this, and the fitted line will give an equation through which you can compute the peak discharge for a given area. So one such equation was given. It is QMP, which is a peak discharge using envelope curve, is 325 into A, 278 plus A, whole is for 0.78. Again, A is in kilometers square and QP is PMP is in meter cube per second. So any questions on this part? Actually, it's directly you have an empirical formula that has been derived based on some statistic relationship, and you can find the peak discharge, and one such way is to determine a relationship with the catchment area. You had note down you have four methods. One is the Dickens method, another is the Rives formula, third is English formula, and fourth is your envelope curve. Now we can do a problem on this. Let's say you have to estimate the maximum fluid flow following the catchment using an appropriate empirical formula. So in the first one, your area is 40.5 kilometers square and it's located in Western Ghats area, that's Maharashtra. In the second, it's 40.5 kilometers area remains same, but this catchment belongs to Gagnetic Plain. In the third, area remains again same, it's a Kaveri Delta, Tamil Nadu. And in the fourth, we have to estimate the peak discharge uh, by the maximum world flood experience. So this is actually your envelope method. So we can start. So first thing what we do is for the Western Ghat Maharashtra, you have English method. And from that your peak discharge is 124 into A divided by under root of A plus 10.4. So if you put the area, which is 40.5 kilometers square, this will be 124 into 40.5 under root of 40.5 plus 10.4. So you get a value of around 704 meter cube per second. Now in the second case, which is the catchment belongs to Gagnetic Plain, and for the Gagnetic Plain, so this equation applies for Gagnetic Plain. Dickens formula, and you can write your QP is equal to CD A raised power 3 by 4, as the catchment belongs to Gagnetic Plain. This is Dickens formula. Now your CD belong is here 6, and your area of catchment is given 40.5 meter cube per second, and you have a power of 3.4. If you compute the value, it will be 96.3 meter cube per second. In the third case, where it's a Kaveri Delta, which is in the Tamil Nadu, for the Tamil Nadu, we studied that we have to use a Rives formula, and for that QP will be equal to CR into A raised power 2 by 3. Now your CR, since this region which is Kaveri Delta, so this is, let's say this is your Kaveri Delta, and this is the distance from the coast. This distance is actually less than 80 kilometer. So in that case, CR has to be taken as 6.8. So we take an CR to be 6.8, multiply with the area, which is 40.5 whole raised power 2 by 3. You compute the value, it will be 80.2 meter cube per second. This is actually Rives formula. Now in the fourth case, you are being asked to compute the discharge using the envelope method, in short, which is also called a world flood experience. So for that case, we know that peak discharge is given by an equation 325 into A divided by 278 plus A 4 raised power 0.78. If you put the value, this will be 3025 into 40.5 divided by 278 plus 40.5 in 4 is 0.78. The value comes equal to be 1367 meter cube per second. This is from the world experience, or you can call it as envelope method. Any doubts here? So if not, then I can then write. So first one is Gagnet. No, sorry. So the first one was Western Ghat. The value was 704 meter cube per second. And then we had Gagnet Plains. The value was 96.3 meter cube per second. Then we had Tamil Nadu, Kaveri. Your value was 80.2 meter cube per second. Then you have envelope or world experience, and your value was 167 meter cube per second. So if we rank them, so this was the highest and this has the lowest value. So this is how empirically we can use the equations or a relationship between the flood peak and area to determine the maximum flood discharge. So any questions till now in this? If not, then I will stop the meeting. Thank you.